So in this numerical, we will use some relation that we have derived in the last class, like the separation of nth bright fringe from central maxima is n lambda capital D divided by small d. This we did in the last class. Now in this question, instead of one single source, two sources are given. Simultaneously, two sources are given. So this is source. This is double slit. And this is screen. So these are two slits, slit 1 and slit 2. There is slit number 1. This is slit number 2. This is your double slit pattern. And this is screen. So from these sources, instead of one light, two light waves are coming. Let's say two different colors are coming, blue and red. Like from S1, you have light of blue color, and from S2, you have light of blue color, and the light of red color and light of red color. So two waves are simultaneously coming from source S1 as well as source S2. At the center of the screen, this one, at the center, the waves from both the slits will reach simultaneously. Waves from both the slits will reach simultaneously. Blue will come, so there will be a bright fringe of blue color. Then also the waves of the red color will reach this point. Waves of red color will also reach this point. And you will get this one, a blue wavefront, a red central maximum. So this is central maximum. Now, if you can remember, for central maxima, yn equal to, we measure our separation from central maxima. The separation of central maxima from central maxima is 0. Central maxima is at origin, yn equal to 0. So at central maxima, you can see two bright fringes are coinciding. One bright fringe of blue color, another bright fringe of red color. In this question, you are supposed to calculate the position at which next set of blue and red bright fringe will coincide. You have to calculate the position of point at which the next red and blue bright fringe will coincide. The first set which is coinciding is the central bright fringe, central maxima. Central bright fringe of blue color and central bright fringe of red color coincide over this point. Now you have to decide that which bright fringe of blue color and which bright fringe of red color will coincide. It may be possible second bright fringe of blue can coincide with second of red, or it may be the possibility that second bright fringe of blue will coincide with third bright fringe of red, or it could be like second bright fringe of blue coincide with fifth of red. That you have to calculate which fringes will coincide. Now, since I don't know the exact number of fringe, that which fringe which coincide first, second, third, fourth, fifth, or whatever. So I'm taking one as the nth fringe. For blue, I'm saying this is the nth bright fringe. And for red, I'm taking mth fringe. So I'm saying that nth bright fringe of lambda 1 will coincide with mth bright fringe of lambda. So nth bright fringe of lambda 1 will coincide with mth bright fringe of lambda 2. I don't know the exact number of nmm, N and M could be 2, 3, 4, 5, 6, 7. I don't know the exact number, so I'm taking one as N and another as M. Lambda 1 is 800 and lambda 2 is 600 nanometer. Wavelength lambda 1 is 800 nanometer. And I'm writing lambda 2 as 600 nanometer. That we know, that lambda, the value of lambda 1 and value of lambda 2. This we know. That lambda 2 is, lambda 1 is 800 and lambda 2 is 600. Now, if both the fringes coincides here, so Fatma, can you relate Yn and Ym if both the fringes are coinciding here? This will be equal, right? Yn will be equal to Ym. So nth you can write n lambda, it's d lambda 1 d by d is m lambda 2 d by d. So this d will cancel this d, capital D will cancel this capital D, and you can write this as lambda 1, or you can write that n is lambda 2 by lambda 1 into m. Now I have to decide the value of n and m for which these fringes will coincide. So let's substitute lambda 2 and lambda 1. Lambda 2 is 600. Lambda 1 is 800. These are in nanometer. I'm not doing unit conversion because eventually they will cancel out. The multiplication factor, here the multiplication factor will be -9. Here again is 10 raised to the power of -9. So they will eventually cancel out each other, multiplied by. So your n is 6 by 8m, or you can say this is 3 by 4m. Now you have to decide the smallest value of m so that both the fringes will coincide. If I take m equal to 1, then how much is n? Possible. Is the value of n 3 by 4 possible?
No, sir.
Why?
Fraction.
Yeah. The number of fringe cannot be in fraction. That means n comes out to be 3 by 4. It's not possible. Means first bright fringe of lambda 2 cannot coincide with any bright fringe of lambda 1. Okay, Fatma, can you guess the minimum value of m for which n is not a fraction, n is an integer? The minimum value of m for which n is an integer? 4. If I take m equal to 4, then your n will comes out to be 3 by 4 into 4. So 4 will cancel this 4, your n comes out to be 3. So m is equal to 4 and your n equal to 3. That means fourth bright fringe of lambda 2 will coincide with the third bright fringe of lambda. So you can say that fourth bright fringe of lambda 2 will coincide with third bright fringe of lambda 1. So now this we know, that fourth bright fringe of lambda 2 and third bright fringe of lambda 1 will coincide. What would be the next pair? If I put m is equal to 8, then how much is n?
6.
Yes, if I put m equal to 8, then your n will comes out to be 6. So this is the next pair of bright fringes that will coincide. But in the numerical, and there would be many, just keep on changing the value of m, you'll be getting the value of n. There are many fringes which are coinciding, but you are supposed to calculate the least distance. So for the least distance, you will calculate the first one, the first pair. The first pair is this. So we will not take these two. Now, if they coincide, then you can easily calculate y3 and y4. You can calculate y3. You need separation. So y3 will be 3 lambda 1. This is n. If I'm taking n equal to 3, n is corresponding to lambda 1. And lambda 1 is 800. So y3 is 3 lambda 1 d by d. Let's just substitute the values. 3 lambda 1 is 800 into 10 raised to the power minus 9 multiplied by capital D. How much is capital D? Capital D is 1.4 and this is small d, 0.28. 1.4 divided by 0.28 into 10 raised to the power minus 3. So if I cancel this thing, this will be 2 zeros and this will give 1 0. This 14 will cancel this 2. This is 400. So your y3 will comes out to be 12 into 10 raised to the power 20 and minus 9 minus 7 and 2 minus 5 minus 5 and plus 3 minus 2 minus 2 minus 1. 12 into 10 raised to the power minus 3. Okay, so Giovanna, can you guess the value of y4? If you're taking wavelength lambda 2, then which fringe is coinciding? Mth fringe. And what's the value of m? It's 4. How much is y4?
4 into lambda 2 d by d.
Yeah, but what would be the final result? Just without calculation, can you guess the final result? It should be 12 into 10 raised to minus 3. See, we are doing this calculation when both the fringes are coinciding. We are taking this equation that both the fringes will coincide only if the separations are same, right?
Yes, sir.
Separation of third fringe from the central maxima of one wavelength is equal to the separation of fourth fringe of the another wavelength. Then only these two fringes will coincide. So if I'm taking this equation here, that yn is equal to yn, if n comes out to be 3, m comes out to be 4, that means your y3 should be equal to y4. If you complete this calculation, what should be the answer?
12 into 10 raised to minus 3.
10 raised to minus 3. This question was in the sample paper of CBSE for some 2 or 3 consecutive years. So it's a bit tricky. But since this was in sample paper, so it's an important question. Given figure, so this is S1, this is S2. This is the perpendicular bisector, which means this is d by 2 and this is d by 2. If you can remember, in the derivation of fringe width, we place the source at the perpendicular bisector, but now I'm placing the source here. This is your source, the source slit, the bulb from which light is coming. This is here. It's not at the perpendicular bisector now. So this is the difference. Let's say this is a point P. You have to calculate again the condition of bright fringe and dark fringe if the source is not at the perpendicular bisector. If source is at the perpendicular bisector, then you know that the condition of bright fringe is this n lambda d by d. But you have to derive it again, the condition of bright fringe, if source is not at the perpendicular bisector. So the question is first part. So let's consider a point P here at a separation y. You're supposed to calculate the equation of yn for which the point P here is a bright fringe and the condition of yn for which the point P here is a dark fringe. We have already derived this thing, but while deriving, we have assumed that the source is at the perpendicular bisector. But now the source is not at the perpendicular bisector, so you have to see what is the difference in the calculations. When we derive it, we have assumed that SS1, S2, S1 is equal to S2, S2, that is SS2. These two are equal. But in the question now it is given that they are not equal, they have a part difference of lambda by 4. So for this, let's take a wave which start from this point S, this is it, and it reach point B. So the distance that this wave is traveling is SS1 plus SS2. This is the distance that this wave travels. Now the another wave that will reach point P through this slit S2 will travel this distance, SS2 plus S2P. So the part difference, Giovanna, can you guess the part difference between waves reaching point P from S? Part difference. I need part difference between waves
Is it
reaching, just a second, reaching point P from S through S2 and S1. So one wave is traveling in this way, another wave is traveling in this way. I need part difference. So the total part that this wave is covering while moving to point P through S2 is SS2 plus S2P. Similarly, the path that this wave is covering to travel up to P is SS1 plus S1P. So the part difference is, you can write this as, this is SS2 minus SS1 plus S2P minus S1P. I call this as equation number 1. Now it is given that SS2 minus SS1 is, how much is it? This is lambda by 4. This is given that SS2 minus SS1 is lambda by 4. So, and if this distance is capital D, this is Y, and this is D, this slit width is D. Fatma, do you remember the relation between this difference yn capital D and small d? This I have derived in the last class. This is a part of derivation. I don't want to derive it again. I have already derived this in the last class. SS2 minus SS1 is, it's yn small d by capital. This we have derived. That SS2 minus SS1 is yn d by d. That n lambda capital D by small d comes from this definition only. To derive this n lambda capital D by small d, we just put that SS2 minus SS1 is n lambda for bright fringe. So this is it. So if I do all these substitutions, I call this as equation number 1, I call this as equation number 2, and I say that this is equation number 3. So if I substitute both the equations, 2 and 3 in 1, if I substitute all equation in equation number 1, then we will get that x is yn small d by capital D plus lambda by 4. Sorry, the first one was lambda by 4. Lambda by 4 plus this thing. This is lambda by 4 and S2P minus S1P. S2, sorry. S2P minus S1. This thing. S2P to P and S1T, S1 to P. This SS2 minus S1P is yn d by d. This we have derived in the last derivation. So if I substitute it here, it's yn small d by capital D. We can calculate this yn from here. Let's take this to the left hand side. This is x minus lambda by 4 is equal to yn small d by capital D. So you can say that your yn is, it's capital D by small d multiplied by x minus lambda by 4. This is y. Now, let's see first part. You need condition for constructive and destructive interference. So for constructive interference, how much is part difference for constructive interference?
X equal to n lambda.
N lambda, yes. So put x equal to n lambda here. Let's call this as equation number 4. Call this as equation number 5. Substitute 5 in 4. When you substitute 5 in 4, that's capital D by small d. It's n lambda minus lambda by 4 is equal to y. You can take this lambda outside. So that's lambda d by d. It's n minus 1 by 4. This is the condition of bright fringe. Similarly, you can calculate the condition of destructive interference. And if you can remember, the part difference for dark fringe is 2n minus 1 lambda by 2. So if I substitute, I call this as equation number 6. I'm substituting this here. This we have derived in the first part of interference, the condition of maxima and minima. So if I can substitute 6 in 4, then the result is d by d. Instead of this, I'm writing 2n minus 1 lambda by 4 minus lambda by 4 is equal to yn. So I can write this as it's d by d, it's 2n minus lambda by 4 minus, no, sorry, not just. So just multiply it here. So that is 2 lambda by 4. It's minus lambda by 4. It's minus lambda by 4 is equal to y. So minus lambda by 4 minus lambda by 4 is minus lambda by 2. So that's d by d. It's 2n. This 2 will cancel this 4, right? So that's lambda by 2. Oh, sorry. Yes, it's lambda by 2. Sorry. Yes, yes, it's no. This is 4. This is 2. This is 4. This is 2. Yes, yes, you're right. This is lambda by 2. This is lambda by 4. So this is 2n lambda by 2 minus lambda by 2 minus lambda by 4. Just a second. So now this 2 will cancel this 2. Minus lambda by 2 minus lambda by 4. How much is this? Lambda by 2, lambda by 4. That's minus 3 lambda by 4, which is equal to y. Next, what we can do is we can take this lambda as common. So this is lambda d by d. So it's n minus 3 lambda by 4 is yn. So this is the condition of minima and this is the condition of maxima if this source S is not at the perpendicular bisector. When this source was at perpendicular bisector, then instead of this, the equation was this n lambda d by d. Instead of this thing, this was the equation. Instead of this, the equation was 2n plus 1 lambda d by 2d. But just due to displacement of this source, the definitions get changed. Okay, now this you will solve. For fringe width, just subtract the separation of nth and n minus 1th fringe. You can take any fringe, bright or dark fringe, you will get the fringe width. And for central maximum, put n equal to 0 in the condition of maxima. See, just for the fringe width, you just have to subtract the separation of nth fringe and n minus 1th fringe. So this is the expression of nth bright fringe, right? So this is part 2. For fringe width, Basically, fringe width is the separation between two consecutive fringes. So I'm taking the separation between nth fringe and n minus 1th fringe. So this is the nth fringe. Expression for nth fringe is this: lambda d by d n minus 1 by 4. So it's lambda d by d. It's n minus 1 by 4. Minus n minus 1th fringe. So instead of n, put n minus 1. So it's lambda d by d. It's n minus 1 minus 1 by 4. So just instead of n, I put n minus 1. Now if I solve it, it's lambda d by d is common. I'm left with n minus 1 by 4 minus n plus 1 plus 1 by 4. Due to this negative sign, all sign in the bracket will change. So it's this n becomes negative, this minus 1 becomes plus 1, and 1 by 4 becomes plus 1 by 4. So this will cancel this. 1 by 4 will cancel this 1 by 4. And your fringe width comes out to be its lambda d by d. So this is the fringe width. You can see fringe width is not changing. The fringe width remains same. In the original experiment, when this source was at the perpendicular bisector, the fringe width was same, lambda d by d. Now again, the fringe width is same. Fringe width is not changing. Last, locate the position of central right fringe. So for the central right fringe, n is equal to 0. This is for nth fringe. For central, put n equal to 0 here. For central right fringe, for central right fringe, put n equal to 0 in condition of central maximum, in condition of maximum. So this is the condition of maxima. Yn is n minus 1 by 4 lambda d over d. So if I put n equal to 0 here, then for central right fringe, it comes out to be 0 minus 1 by 4. It's lambda d by d. So your central right fringe will be at minus of lambda d by 4d. This is the position of your central right fringe, minus lambda d over 4d. This negative sign here means this is the origin from which we measure our positions. So central right fringe is not at the origin. It's not at the midpoint. This is here. This is your central right fringe. And this separation is your y0 that we have calculated. So if you modify Young's double slit experiment in a way that source is not at the perpendicular bisector, then the central bright fringe will not lie at the center. It will lie just below the center, this much distance below the center. Next, we are left with two types of conceptual questions. The one is, what will happen if in Young's double slit experiment, instead of a monochromatic source, I'm using white light. Monochromatic source means source having a single wavelength. Means I'm using laser of red color. So from both S1 and S2, I'm using same red color. But now I'm repeating Young's double slit experiment. Young's double slit experiment with white light. Young's double slit experiment with white light. So say you have two slits, S1 and S2. This is slit S1. This is another slit S2. Earlier, when we studied Young's double slit experiment, The light that is coming from source S1 and source S2 is monochromatic. Monochromatic means of a single wavelength. Means if red color is coming from here, then red is coming from here, no other color. But now I'm saying the light is white. The red color I understand, blue I understand. What do you mean by white light? How many colors this light have? White light has 7 colors. White light means if all colors from violet to red, if all colors from violet to red mixed up, then they form white color. Okay, so white is basically the combination of all color. When I'm saying white light is coming, that means all 7 colors are coming. So from here, white light is coming, that means all these colors are coming. All these colors are coming. Now, you have to decide what type of pattern one will get. So when I say white light is coming from both the slits, so think like 7 colors are coming from this slit and 7 colors are coming from this slit. So how many interference patterns are you expecting? 1 or 7? So from both the slits, 7 colors are coming. 7 from this and 7 from this. So we'll have 7 interference patterns. The central bright would be at the center, the bright fringe of all 7 colors will coincide. So central bright fringe would be white. The next fringe would be violet. And after few, like next will be indigo, after few colors, the interference pattern will disappear. The reason is after few bright fringes, the bright fringes of different colors starts overlapping. Like orange will overlap with green. The bright fringe of maybe yellow can overlap with the red. Due to this overlapping, the fringes will disappear. You cannot see interference pattern beyond some 3 or 4 bright fringes. So since we have already done this topic, so I'm not writing it. So the thing is, if you are using white light, then the central bright fringe would be white and all other fringe will be, the next will be violet, then it will be indigo, and after few fringes, the bright fringes will overlap and the interference will disappear. So that means interference is over. The next topic is diffraction. The next topic, the wave optics. The next thing that I have to start is diffraction. See, what is diffraction? Diffraction is basically the phenomena of bending of light. When light passes through an obstacle, it bends from its corner. That bending is known as diffraction. Okay, just tell me one thing. The bending of light is new for you. Have you observed bending of sound? What do you think? Sound bends or not? Does sound waves bends? Yes, it's a very common observation, right? If I take a wall, like this always happens if I take a wall. It's a soundproof wall. I put a speaker here. The speaker is emitting sound waves. And I put a listener here. Then obviously sound cannot travel in this way. This is a soundproof wall. This wall is soundproof. Soundproof wall. This wall is soundproof. So the person standing here cannot listen what is saying. But the waves will travel here. Then it will bend from the corner and then these waves will reach this also. So that's basically bending of sound. And that bending of sound is diffraction in sound. For bending, there is one condition, and that condition is the corner, this corner. The corner from which sound is bending. The size of this corner should be of the order of wavelength. Means that the wavelength of sound is 3 into 10 raised power minus 6. Then the size of the corner should be of the order of 10 raised power minus 6. Then only this can bend the sound waves. So sound wave, this is very common because the wavelength of sound waves is pretty large. It's 10 raised to the power minus 2 or 10 raised power minus 3. You can easily get the corners of this size. So usually these corners, the size of these corners are of this order of the wavelength of the sound. So these corners can bend sound waves. So this diffraction in sound waves is very common. But in light waves, it's not a common phenomenon. The reason is the wavelength of light is very small. The wavelength of light is this 10 raised to the power minus 7 meter. So the corners or the obstacles of this order is hard to find. You find very rare cases where the size of the obstacle is this 10 raised to minus 7 meter. So the diffraction in light is not a very common observation, but yes, in sound you observe it daily in your day-to-day life. So I'm just rubbing it. So what is diffraction? Diffraction is, it is the phenomena of bending of light from obstacle or aperture placed in path of light. Due to bending, light can penetrate into the geometrical shadow. See, one example of observing this diffraction in light is this. Let's say I take this obstacle. This is a wall. It's a wall. And this is the screen. And I'm incident light waves here. All over here. So this is a wall. Light cannot penetrate a wall. Wall is opaque. So this is wall. Light cannot penetrate it. Okay, just tell me, in this region, like this region behind the wall, this whole region, in this region, what are you expecting? Are you expecting light waves here or shadow here? What are you expecting? Light waves or the shadow of this obstacle? Yes, in this region, we expect the shadow. This should have shadow, right? Because light cannot penetrate the wall, you will have the shadow of wall. But you may observe that some light waves are reaching into the point where you were expecting the shadow. Some light waves will reach this point where you will initially expecting the shadow. So the light waves are basically penetrating the shadow. But if you think of light as something which always travels in a straight line, then light should not penetrate in the shadow. It should rather move in the straight line here. But due to diffraction effect, this light gets bent and it penetrates into the geometrical shadow. This is what we call diffraction. Now, how strong this effect is means how much this light is bending depends upon the size of the corner. These corners are very, very sharp, like the edges of a blade. If these corners are like the edges of a blade, then this bending is very large. But if the corners are not very sharp, they are very thick corners, then bending is very small. It may be that you don't even observe these type of things for a very thick wall. But if corners are very sharp, like the edges of a blade, then this diffraction will be prominent. For diffraction, it is important that the corner or the obstacle from which the light waves are diffracting, the size of that obstacle or corner should be comparable to the wavelength. If it is less than the wavelength, that's very good. Otherwise, it should be at least equal to the wavelength, comparable to the wavelength of light. This is diffraction effects. Now, what happened? Only a single light wave is not coming. A number of light waves are coming from here. So what happened? All these waves starts to overlap, or I should say that these waves will start superimposing. Due to superposition, you will get some bright and dark pattern, just like you got in interference. But unlike interference, these patterns are not very, they don't have very good contrast. Like in interference, bright were very bright and dark were very dark. Means there was a very good contrast between bright and dark fringes, but in diffraction, you don't find such contrast. There's not a very good contrast between bright and dark fringes. There are plenty of differences between this diffraction and interference, but the common thing is, even in interference, light waves were superimposing. In diffraction too, light waves are superimposing. But the conditions were different. In interference, light waves from two coherent sources were superimposing. But in diffraction, there is one source. The light waves are bending and they are superimposing with each other. So that is diffraction. There's one more condition for diffraction. That size of aperture for diffraction, the size of aperture should be less than the wavelength. Less than or comparable to the wavelength of light. Comparable to the wavelength of light. To the wavelength of light. So this is, okay, I'm repeating it again. So in this experiment, what we do, we take a single slit, a slit of a very narrow width. We allow light waves to pass through it. When light waves pass through it, they bend. Due to bending, these waves superimpose with each other, and on the screen, due to this superposition, you will get bright and dark fringes. At the center, you get central bright fringe. Then just after central bright fringe, this is first minima. This is central maxima, then first minima. After first minima, this is first maxima, then second minima, then second maxima, and all. The fringe width are different. The width of the central bright fringe is maximum. It's very wide. Then the width of other bright fringe keep on decreasing. One more thing, central bright fringe is very bright. Its intensity is very high as compared to the intensity of other fringes. So basically, you have to calculate this pattern. You have to calculate the conditions in terms of part difference for which you will get central maxima. You have to calculate conditions in terms of part difference for which you get these maximas. You need condition for these minima, conditions in terms of part difference. Then they will ask you to calculate the width of this central maximum. Supposed to calculate this width of central maximum. Okay, so before starting this single slit diffraction experiment, see the types of diffractions. Types of diffraction. You can divide diffraction into two major types. We have two major types of diffraction. One is Fraunhofer, or say the first is Fresnel diffraction, another is Fraunhofer diffraction. In Fresnel diffraction, the separation between the source slit and the screen is finite. Sorry. In Fresnel, the separation between light source, slit means that opening from which the light waves are passing, and screen is finite. If all separations are finite, then the diffraction is Fresnel diffraction. In Fraunhofer diffraction, all these separations are infinite, means the separation between source, slit, and screen, all the separations are infinite. Separation between source, slit, and screen are infinite. All separations are infinite. If separations are infinite, then the diffraction is Fraunhofer. If the separations are finite, then the diffraction is Fresnel. Now, if separations are infinite, that means source is at a very large distance. So the wavefront here is plane wavefront. So in Fraunhofer, you deal with plane wavefront. Wavefront is plane. This we did in Heinz principle, that if source is at a very large distance from the observer, then the wavefront will be a plane wavefront. You will observe a plane wavefront. Wavefront would be plane. Just note it down. Fresnel is not a part of your syllabus. You have to study only Fraunhofer diffraction. Now, single slit diffraction. Single slit diffraction. The same experiment that I have just shown. Single slit diffraction. So the experiment that we just have discussed, this is source and this is Fraunhofer. This is your single slit. This is the single slit. For Fraunhofer, the separation between this source and single slit should be infinite. They should be at infinite separation from each other. So the reason to have infinite separation is we want to have plane wavefront. We want to have parallel rays. So to get parallel rays, we have two types of tricks. The one is you can place your source at infinity, so the rays coming will be parallel. Or what you can do is you take a convex lens. This you must have done in class 10 physics. You take a convex lens, decide the focus of the convex lens. If you put your object at the focus, then after refraction from the lens, the rays becomes parallel. And parallel rays means the rays are coming from infinity. So for parallel rays, you can do two things. Either you put your source at infinity at a very large distance, so that rays coming from the source are parallel. Or what you can do is you can put your source at the focus of the convex lens, so that after refraction from the lens, your rays becomes parallel. So here I will use the second trick. What I will do, I will take a convex lens. This is my convex lens. And I put my source at its focus. This is the focus of convex lens. This is the focus of lens. I take a convex lens and put source at the focus of the convex lens. So what happens is, after refraction from the lens, rays will become parallel. This is what happens. After refraction from the lens, rays will become parallel. The wavefront will become plane. After refraction from the lens, what will happen? The rays becomes parallel. And this is what you want to achieve. You want to achieve parallel rays and plane wavefront. So you're getting parallel rays and plane wavefront. So this is how we practically achieve plane wavefront in lab. We just place the source at the focus of the convex lens, and the wavefront that we get is a plane wavefront. So this is the plane wavefront that I am getting. This is AB. This AB is my incident plane wavefront. Or simply take this as waves that you are having parallel waves from here. When these waves will pass through this single slit, and I'm taking the size of the slit equal to the wavelength. When these waves will pass through these slits, these waves will get bent. They will get bent into different directions. So some of your waves can travel still in the straight line. Means they're not bending, they're traveling straight line. Some will bend at some angle, some are bending in this way. Few can bend even in downwards direction. So randomly, when the waves pass through these slits, they get bent in every possible direction. What we have seen in that experiment. And when they bend, they try to superimpose each other. When they superimpose each other, they give rise to maxima and minima. They can either superimpose constructively. Constructively means waves will add up to wave, or they can superimpose destructively, means wave will cancel the wave. So this is what happened. So these waves will get bent. These waves get bent. And when these bent waves superimpose each other, they will give rise to the superposition of waves. Now, since after bending, even after bending, the waves are parallel. The parallel rays will meet at infinity. So to converge these waves at a finite distance, I'm taking one more wave. Okay, I'm taking one more wave from the center. Now I want to converge all these waves at a finite separation. This is just random bending of light. The light waves enters, the size of the slit is comparable to the wavelength, they gets bent in random directions. So I'm just taking two directions. One which does not bend, another which is bending at some angle. I call this angle as theta. From the original direction, it's making some angle theta. But the issue is these waves will meet at infinity because they are parallel. Now, if you want to converge these waves at a finite separation, then what you will do, you will take another convex lens. This convex lens will converge these rays. So I have to, this convex lens will basically converge these rays. You know that convex lens is converging. Even I have discussed this converging nature of convex lens in Heinz principle. So what will happen is when these waves passes through the lens, they will get converged. So I'm choosing the focal length of the lens in a way that all the waves gets converged at the screen. So this gets converged here, this gets converged here, this gets converged here. They gets converged here, they gets converged here, they get converged here. And when these waves get converged at a point, they meet, means they superimpose, and you will get fringes. This point here that I have chosen is the midpoint. This is where you will get that very bright central maximum. So this is your central maximum. This is the position of your central maximum. That very bright fringe. Central maxima, and this is the center from which we measure all distances. This is the center of central maxima from which we measure all distances. The point here, well, these waves are combined. Here you can get a maxima or you can get a minima. Well, that depends upon the part difference. If part difference is of maxima, then you will get a maxima here. Well, waves gets added up. If part for another value of part difference, you can get a minima here. Waves will get cancelled out each other. So at this point, you get some nth fringe, some nth fringe. I don't know whether it's bright or dark. You will get some nth fringe. This is point B. In diffraction, we usually don't write this fringe. So I'm not writing fringe. I'm just writing this is point B. You will get a fringe here, some spot here, bright or dark spot. No. This slit width is A. So the experiment is clear. Waves are coming, they are passing through the slits, they are bending at different angle. You are using a lens to converge them in on the screen. Now to decide whether this point P is minima or maxima, you need part difference. I call this point as P1, not P1. I call this as C. I call this point at D. So the waves at P are coming from C and D. Okay, Fatma, can you just tell me out of waves are coming at P from C as well as D? Which set of waves are covering more path? The wave from C or wave from D?
From D.
From D, yes. They are covering large distance, right? The next task is to calculate the part difference. I need part difference. I need part difference between waves reaching point P from C and D. So I need that part difference. To get that part difference, what I can do is, see this much distance is A. Okay. I'm dropping a perpendicular from C to this line. So what I did, I drop a perpendicular from here. This much portion of DP that I have cut, this NP is exactly equal to CP. This leftover is the part difference, is dn. This dn is basically the part difference. This is the part difference. So we can easily calculate this part difference. Let's say I call this angle as theta n. This angle is theta n. So we can easily calculate this dn from this triangle if we know that CD is equal to A. So here A is basically slit width. The slit that we are using, this is the width of that slit A. So if I take this triangle in triangle CDN, I'm using sine theta n. How much is sine theta n? Sine theta n is perpendicular upon hypotenuse. It's dn divided by CD. So you can say that your sine theta n is dn divided by CD. And how much is CD? CD is your slit width. So this is your dn, your part difference A sine theta n. We will need this part difference for the conditions of all bright and dark fringes. So this is basically the differences path of wave reaching point P from point C as well as point D. Next, we need conditions for the bright and the dark fringe. See, for the bright or for the central maximum, this part difference should be, first let's write condition for, just one more thing. There are few more things that we can calculate. See, what is theta n here? The theta n will tell you the position of fringe. So if you're taking a fringe here, yes, Jubena, if I'm taking a fringe here, let's say I'm taking a fringe Q here, how this theta will vary? Theta will remain same, it will decrease or it will increase. If you're taking a fringe here, this
It will increase.
it will increase. So this theta basically tell you the position of the fringe. So we call this theta as angular fringe separation. This will tell you the separation of fringe, angular fringe separation. You can even calculate this linear separation, the separation of nth fringe from the central bright fringe. You can also calculate this yn. Yn is separation of nth fringe from central maxima. And then we can use capital D, which is separation between slit and screen. Separation between slit and screen. This is the separation between slit and screen that we call capital D. This is my capital D. This is capital D. The separation between slit and screen. So what we can do is, if I take this triangle, let's call this as point A, B, C, D, E. I call this as point E. This is O and this is P. In EOP, right angle triangle, you can calculate tan theta n. In triangle EOP, I can write that tan theta n is perpendicular, which is yn, divided by base, which is d. It's yn over d. So you can write that yn is d tan theta n. So if theta n means angular fringe separation is known, you can easily calculate the linear fringe separation. One more thing. If I'm considering small angle approximation here, small angle approximation. If I consider this approximation, that angle is small, angle is very small. For small angles, remember, tan theta n is almost equal to theta n, as well as sine theta n is almost equal to theta. This is small angle approximation. For small angles, the tan theta is equal to theta and sine theta equal to theta. So here, this tan theta n could be written as theta n. So you can write that this thing, it's just d into theta. If your angle is small, then you can use this small angle approximation, that linear separation is just d into theta.